Hi everyone, this week we are in for the big chunk of the course. We are going to talk about machine learning methods for economics. As I mentioned previously, regression is a form of machine learning, but here I will tackle the recent algorithms that are called machine learning, and I will look at their applications in economics. First, a little disclaimer. I do not legally allow this content to be published without my consent, and I will take this content down if I see it online and report whoever uploaded it. So before I get into the outline, let me remind you what I showed in the first lecture about what machine learning is. If you remember, I mentioned that there are many definitions, and let's start with Wikipedia. Machine learning is the study of computer algorithms that improve automatically through experience. It is seen as a part of artificial intelligence. Machine learning algorithms build a model based on sample data, known as training data, in order to make predictions or decisions without being explicitly programmed to do so. Another definition is more formal and says that a computer program is said to learn from experience E with respect to some class of tasks T and performance measure P if its performance at tasks in T, as measured by P, improves with experience E. If you think about selection models, the model selection lecture, we already went over something similar. A class of tasks would be, for example, being good at predicting. A performance measure could be, for instance, the test MSE or some sort of cross-validation criterion. And E would be the number of times we are doing it. So, we said a program is said to learn if, after being submitted a large amount of data and after repeating the same process over and over, the performance measure P increases, so the performance increases, as in, for instance, the minimization criterion decreases as we increase the amount of experience. Self-driving cars use AI systems. The automatic vision system that identifies an imminent accident is machine learning, based on past experiences, based on recognition of the road, of the marking on the road, of cars in front and behind and on the side. Based on all these past experiences, the prediction or the decisions are getting better and better because the algorithm is learning from experience. So as you feed more and more data to the algorithm is able to make better, is able to provide a better performance, whatever that performance might be. Well, we won't talk about self-driving cars today, unfortunately. We are in the realm of economics and econometrics, so we will mostly talk about data and regressions and causality and predictions. So, that's going to be a pretty chunky lecture. So first, I'm going to talk about supervised learning. Remember, supervised learning is a case of learning where there is a variable that we want to explain or predict, like a variable y, by some variables x. In supervised learning, we already went through regression problems before, but now we're going to go through the machine learning algorithms used for regression problems. In particular, I will talk about regression trees and bagging, random forests, which are related to the concept of a regression tree, boosting as well, and then I'll talk about neural networks, which are a very different concept, but they can be used for regression problems. I'll also talk about classification problems. So those are not problems that I have talked about so far. Pretty much classification problems answer the question of what if y is a binary variable. we went over the case where x is a binary variable, like a treatment variable, or a smoking status variable, or a gender variable, or and so on. What happens if the variable y, the one you want to predict or estimate the marginal effect on, is binary or maybe has multiple different values? What if it's a yes or no variable? What if it's a blue, green, or red variable? I will briefly talk about what linear and logistic regressions can do, but it won't be the focus of today's lecture. I will mostly talk about classification trees, the same way I will talk about regression trees. The similar concept can apply to classification problems by changing a couple of things here and there, but the idea will be the same. And then I'll talk about something entirely different called support vector machines. Pretty fancy. Then I will touch on unsupervised learning. So what happens if we don't have a y, but rather we want to understand some relationship between the x's, some patterns. I will talk about something we already know, principal components. And I will talk about clustering, which is a different idea, an entirely different idea than principal components. You guys ready? Let's go. Oh, well, before we go, most of what I'm going to talk about today is in chapters 8, 9, and 10 in Introduction to Statistical Learning with R. I will also use some of their examples in R to show you graphically how these methods are illustrated, but I will talk about this in more detail next week in the Introduction to R. So let's get into supervised learning. So, supervised problems are the most frequent ones for an economist. We went over linear regression before, and we talked about instrumental variables. We talked about generalized least squares, so OLS, IV, GLS. And they can be used for either the purpose of estimation or prediction. For estimation, we talked about OLS, IV, and GLS as a way to consistently estimate the parameters of interest. For prediction, I briefly touched on other methods, in particular in the model selection lecture, where I talked about selecting which variable, how many variables, or maybe lowering the dimension of the variables to use. That's where I talked about principal components, for instance. But in this lecture, we will focus on prediction problems in particular. So we won't be too interested in understanding the marginal effect of one variable on a variable x on a variable y, but rather we will think about what are the relevant x's to predict y well. So, as a throwback to the model selection lecture, flexibility will be a major asset for finding the optimal bias variance trade-off. Remember that all these ridge regression, lasso regression, best subset selection, AIC, BIC criteria, and principal component regressions, partial least squares, all these methods were used as a way to choose the optimal amount of flexibility. So for regression problems, I will get to trees and neural networks. All the things in between that I talked about in the outline are specific to trees. So let's get into the trees. What is a regression tree? First of all, it is one of the most straightforward, easy to implement machine learning algorithms. In fact, it's even easier than understanding what OLS regression does. To be honest, I would not be surprised if regression trees were taught before even teaching linear regressions. It is also very visual and easy to explain. So if you have to work on a prediction problem for your boss, I suggest you to look at regression trees as a good way to explain to your boss how the results were found. So the idea is to build a tree. But tree diagrams are actually called dendrograms, just to make it sound fancy. Tree diagrams. They're used for prediction problems, and in particular with a lot of covariates, the big data problems. So the principle is to start at one big node where all the data is, and in particular all the x's are. And then you make binary splits. So you divide your node into two branches every time, according to some values of the covariates, according to some x's. So then it creates two regions, two nodes, and each observation is going to fall on either one node or the other. Okay? Then the prediction for one observation will be the average of all the observations in the same group, in the same node. So the whole problem here is, how do we make the splits in a good way? And what's a good way? Imagine, to put things in perspective, that we want to predict somebody's income based on a bunch of characteristics. Well, we could use a linear regression. We could regress the log of the wage on things such as experience in an industry, experience with the firm, age, marital status, gender status, and other things. This has been extensively researched in economics, what determines earnings in general. We have leads on major variables, but we always had the same problem of endogeneity. Some of these variables are endogenous in the sense that they are correlated with the error term. That creates an issue when we want to estimate the impact of, let's say, one more year of schooling on your earnings. But here we want to predict, not estimate. Imagine we have a sample of data where each observation is an individual for which we observe income. It could be the wage or the log of the wage, or income more generally, which includes wage and other sources of income. We can observe age, gender, and number of kids. Imagine this is all I have. So age, gender, and number of kids will be my x's, 3 x's. My income variable will be my y. We want to predict income, so we are going to build a tree based on the 3 characteristics I have at hand. For instance, in building my tree, the tree might make a binary split at observations where the age is lower than 30 and where the age is bigger than 30. In this case, the split will be made into 2 nodes, and all the observations where age is lower than 30 will be in one node, and all the observations where age is bigger than 30 will be in the other node. So that opens 2 branches, but why stop there? Then we can do another binary split at each node, and it could be using another variable. In fact, on one node versus another, it might not even be over the same variable. We're going to look at a way to select the relevant variable to split over. You can imagine that selecting the variable age and selecting the value 30 was not random. We want to make an educated guess about where the split should be made. Why 30 and not 25 or 40? Why age first and not gender or number of kids? So, in the left branch, imagine that I make another split. The left branch is the branch where age is lower than 30 years old. The first branch. Imagine I make another split and I distinguish observations where the number of kids is lower than 1 and where the number of kids is bigger than 1. that opens 2 more branches. But on the right branch, it could be that the appropriate split to make is over the gender variable, male versus female. So then that would open overall, that would lead to 4 nodes. We have people younger than 30 years old with less than 1 kid, people younger than 30 years old with more than 1 kid, people over 30 years old which are male, and people over 30 years old which are female. Each observation will fall in one of these nodes. The final prediction of the variable income for individual I will be all the average income of all individuals in the same region as Mr. I. So we have 4 regions, 4 nodes, and we're going to get 4 predictions, the average income in each of them. So if now you come to me and say, oh, I have this observation, it's a new person which is not in the sample, with that many kids, that age, she's a female, and that much income, or maybe not that much income, can you predict the income of that person? Then I would look for which node that observation would fall in, and once I find the node, I look at the corresponding prediction of the node, and I would say, a woman older than 30 years old with 2 kids, I predict, or my tree predicts, that her income will be $100,000 a year. Okay? Now, let's get into how we make those splits. And how we decide on the value of the variable to make a split over. And then there is the other question, how complex do we want our tree to be? After all, I could be, after I get my 4 regions, I could make more splits over age again. Among the ones who are younger than 30, I could also distinguish the ones who are younger than 25 and older than 25. And so on and so forth. And in fact, I could make as many splits as I want and end up with as many nodes as they are observations. So each observation has its own node. But you can already imagine that this is the same as overfitting. And you know what our opinion is about overfitting. We want to limit that. So we're going to have to solve a couple of questions. Which variable to make a split over? Around what value? And how complex do we want our tree to be? Well, like for the OLS estimator, we want our predictions to be as close as possible to the actual data on average. We have a training sample. We want our predictions to fall not too far from the actual data. So, define 2 regions, R1 and R2. They both depend on 2 variables, J and S. S is going to be the value of the cutoff, where the split is made. J is going to be the corresponding variable where the split is made. So R1 of JS, first one, is the set of all the x's such that the variable xj is lower than s. So in my previous example, this is the set of all the observations such that age is lower than 30. And the complement region is going to be the region where all the variables are such that age, all the observations such that age is bigger or equal to 30. Note that here, if I have a strict inequality, then here I have a large inequality. Those 2 regions do not overlap. And this is why one observation can either be in R1 or in R2, but it cannot be in both regions at the same time. So then we are going to define the residual sum of squares, but instead of using our linear model like we did before, we are going to look at the predictions coming from the tree. Well, I want to decide on where to split, so which J to choose and which S to choose. Those are the two things I want to choose, such that in my first region, the predictions I'm going to get, y hat R1, which is one prediction, the average of all the y's in that region, is not too far from all the observations, all the y's in that region. Which is why here you see I, such that xi belongs to the region. So I look at all the observations inside R1. And I want these observations to be close to the prediction. Of course, I take the square because I care about the distance. And I sum it up because I care about the average distance. And since I have two regions, I'm going to do the same thing for the other side. R2. In fact, here it's a typo. It should be R2. My bad. So, the computer can just loop over every variable and every possible value in the data and compute the residual sum of squares every time until it finds the best split. The split that minimizes this residual sum of squares. It is pretty straightforward. You just program this on a computer to go to loop over many values. It is not very time consuming with our current computing power. In fact, there are also ways to program this minimization problem more efficiently, but that's not something I want to get into here. So, here is the algorithm to grow a tree. Find the variable xj and the threshold value s that minimizes RSS. The most straightforward way is to loop over all possible covariates and values. And you check every time. Then you make the split according to the selected covariate and threshold. Once you have your split, you repeat by taking maybe another variable. After making a split over the variable age, you can now move on to either gender or number of kids or something else. So you're going to repeat those steps as many times as you want. And by as you want, I mean until each region, each terminal node, because they're going to be the final nodes at the bottom of the tree, until each node has maybe less than a given number of observations. Remember that we take an average in these nodes. So we don't want to take an average of 2 observations. That's way too overfitted. Rather, you might want to take an average of at least 10, 20, 30 observations. So that's a limit you could set so that you grow your tree until once you have a leaf or node that has less than 30 observations, you stop there. Otherwise, your tree would get too complex. And then you compute the predictions by taking the average of the outcome variable, the average y, for all observations in a terminal node, which we also call a leaf. Pretty straightforward, isn't it? And pretty insightful. Now, I talked about the complexity of a tree. How can we make sure that we are not making our tree too complex? There have been many refinements to avoid overfitting, and one of them is called pruning. Pruning is this activity of cutting, trimming the branches, and so on. Like pruning a bonsai, for instance, when you have a little plant, and every now and then you trim it to make it look good. I don't know much about plants, so don't ask me more about that. So, a highly complex tree, many splits, each leaf has a small amount of observations, again, will predict the training data very well, but the test data poorly due to overfitting. The eternal problem. Imagine the extreme case where a tree has as many leaves as it has observations, so each observation has its own leaf. In this case, prediction is perfect. The average of one value is equal to the value itself. So, you would perfectly predict everybody's wage in your training data. But it is clear that in real life, you might meet somebody who has exactly all the same x's as you and yet doesn't have the same y. This tree, this very complex tree, would do a poor job at predicting that person's wage because it would simply use your wage as the prediction. And that model will feature a high variance. Remember, the variance of a model refers to the volatility in the predictions when fitting this model on another data set than the training sample. So, pruning consists in trimming some branches of a very, very large tree, and you cut here and there. Imagine that this tree is called T0. That's the most complicated tree you can think of. So, overfitting at the maximum. And then, little by little, here and there, you're going to cut some branches to make the tree smaller, the same way you would trim your plant. How do you achieve that? How does a computer achieve that? Well, let's include the penalty term. We've seen in the model selection lecture that a penalty term in general is a good way to mitigate overfitting by including the fact that too high of a complexity or too high of a flexibility will increase your criterion function. So, let alpha be a non-negative number. For each alpha, you're going to look for a tree, T, that minimizes the following quantity. As before, we have the sum of the residuals, the sum of squares residuals. But here, I sum it also over M. What is M? M is the region that I'm putting my observations in. In the previous example, I had two regions, 1 and 2. And then I was doing the same thing on each of them, and so on and so forth. Here, I'm going to add all the predictions of over all the regions at the same time, of the final one. But I have my penalty term here, alpha times the cardinal of T. This absolute value here is referred to the cardinal. Here it refers to the size of the tree. It refers to the number of terminal nodes. So if cardinal T is high, then I have many, many nodes, many leaves. So I am likely to overfit, and my sum of square residual criterion will be high. So this is the penalty term to penalize trees which are too detailed, too complex, too deep. You might hear some of these terms if you look at some resources online. So the inner sum is the sum of square residuals within the leaf Rm. The outer sum adds these sum of square residuals over all the different leaves. And finally, the last term penalizes complex trees. Trees with a high number of terminal nodes, absolute value of T, or cardinal T. This notation is used for sets in general to determine the size of a set. For instance, if I tell you the set that includes number 1, 2, 3, 4, 5, 6, then the cardinal of this set, or the size of this set, is equal to 6, because I have 6 separate elements in it. Now, what I can do is, for each alpha, and I can make alpha go from 0 to, let's say, 20, I make a grid, 1, 2, 3, 4, 5, all the way to 20. Every time I have an alpha, I can put it there, and I can look for the optimal tree, the optimal pruning, according to that corresponds to that level of the penalty term. By now, you should guess that if alpha is equal to 0, we are back to the original problem, where we can overfit, we can make the tree deeper and deeper and deeper, and always decrease this criterion. The same way we can increase the R squared in a linear regression. Same idea. The case where alpha is very big, let's say alpha is equal to 20, will correspond to a huge penalty. As soon as you have a tiny bit amount of nodes, when you multiply this by 20, your whole criterion function will be huge. Now, we need to know what alpha is the best. In order to find alpha, you guessed it, cross-validation. Every time you see a parameter like this, which we call a tuning parameter, think cross-validation. Almost all the time. Not always, but almost all the time. So if you have to make a guess, go for cross-validation. It's close to the best guess you can make. Or validation sets. Test versus sample data sets. So here is how we prune a tree. First, we grow the biggest tree with many terminal nodes. Then we make a grid of value for alpha. Let's say 0 to 20. And for each alpha, we compute all the different sum of square residuals. We compute this criterion by cutting a branch, cutting another, and so on and so forth. We try all the different combinations that minimize this criterion. That will give us, for one alpha, it will give us the best tree, the best subtree. Now, if we have 20 alphas, which subtree is the best? So now we need to find the optimal alpha. And this is where the cross-validation is going to come in. Well, divide the sample into k folds. K is equal to 10 is a standard split. Then repeat the first two steps on all the folds but the kth one. So you grow a big tree on 9 folds out of 10 and you do the pruning. Then you do the same thing on all the other ones. So on the first 9, for one alpha, on the first 9 folds, find the best tree, the best subtree. On the next 9, on the next 9, and so on. Finally, evaluate the test mean squared error on the fold that you left out. And you repeat. You do this for alpha is equal to 1, do all these things. Alpha is equal to 2, all these things. And every time you get an average test MSE. So if you have 20 alphas, you're going to get 20 different test MSEs. You look at the smallest one, and the smallest one will give you the best alpha. Once you find your alpha, you go back to your T0, your biggest tree, and you say, now this is my alpha, let's prune it one more time and see what the best subtree is going to be. Then you're done. In terms of programming, that might seem confusing because you have to pretty much make a loop inside a loop inside a loop. But conceptually, I hope that by now things are clear. Because we're going to talk about cross-validation again today. So let me know if you want me to repeat or re-explain the principle. I really ask you to understand the principle, not exactly everything in detail. Okay? I just want you to understand the idea of what cross-validation does. Let me know in the chat if you have any questions. Okay. Now, pruning is great because using one sample, we can make one big tree and find the best way to trim the branches. And then we make our predictions. Give me any data, any new data, and I will make my predictions using my tree. Okay. This is how it looks like in R. There's a data set called Boston that records a bunch of different things regarding some crime data. And I believe that the variable of interest, MEDV, I believe it's a crime-related measure. And here is what the tree is going to do. We have 200 observations, and we do not have many variables, which is why the tree is not very complex. We start with 100% of the observations, everybody in the same tree. 22 is the average Y, is the average value for MEDV. So that's the prediction if your tree stays there. Then the first split is going to be made over the variable RM. And 88% of the observations are going to go to the left, and 12% of the observation are going to go to the right. And you can see how the split is being done. Here are the predictions within each of your new nodes. The prediction is 19 here, and the prediction is 39 here. Then here, another split is being done using the same variable called RM. And one split is done with 6% of the observations, and the prediction is 33. And the other split with the remaining 6% of the observations for that branch, and the prediction is going to be 45. You can see how by doing the splits, we isolated the high values for the dependent variable, and you can see that now the prediction is 45 as opposed to 39 before and 22 before. And you can see that if I go to the left, my predictions also way smaller. That's because using this variable allowed me to distinguish, to be able to improve my predictions based on this variable. On the left, the next split was not done over the variable called RM, but over the variable called LStat. If LStat is bigger than 14, then we go to the left. If it's not bigger than 14, we go to the right. You can see here, left means yes. Yes, it's smaller than 7, and right means no. So here, yes, yes, on the left, we're going to have yes in the sense bigger than 14, and on the right, we're going to have no in the sense strictly lower than 14. Again, out of my 88% of my observations, 34 will end up on the left, 53 will end up on the right, and then I move on to another split. Turns out here, the variable RM will again be used to make a further split, so that we have 44% of our total observations in this node for prediction of 21, 9% in this node for prediction of 28, and from 34 here, the variable crime, I guess, is going to be used for a split. Once here, no further split is needed. Otherwise, that would be overfitting. That's the idea. Here, however, with 24% of the observations, it seems that another split would be welcome, would be relevant. Age? Well, yeah. Is age bigger or lower than 94 years old? Well, I guess that's something we should check into data first, because 94 seems to be a pretty extreme value for a cutoff. But it turns out that we have 12% of the observation which are younger than 94 years old, and 12% which are older than 94 years old. if you sum up 10%, 12%, 12%, 44%, 9%, 6%, and 6%, you get all of your observations. Each observation is in one of these terminal nodes or leaves. These are what we are going to use to make prediction. Throw me an observation with RM equal to 6, LStat bigger than LStat equal to 15, and crime equal to 12, then we have RM equal to 6, we go here. LStat equal to 15, we go here. Crime equal to 12, we go here. And the prediction for that observation will be equal to 10. It is, I believe, visually pretty straightforward, right? I'm sure you can explain this to somebody who doesn't know what a linear regression is. But if you want to tell him what linear regression is, you might have to take a solid 20 minutes. Here, you can just say that the algorithm is making splits in an optimal way. You don't need to explain exactly what optimal means, but you can say so that the predictions are as close as possible to the data. And then you go. Note, by the way, that RM being used so often shows that this variable is a good predictor of our Y variable. The fact that it is used twice, so that one split is not even enough, another split is needed to improve prediction, means that this variable is highly correlated with the dependent variable. On the other hand, you might end up with trees that do not use some variables, because some of these variables do not help improve your prediction accuracy. There could be variables which are not related to the outcome variable at all. Because they are not, then you can find all kinds of observations with high and low Y, very high Y's or very low Y's, and at the same time have the same value for that specific covariate. So what's interesting is trees also select what variables are going to be relevant for prediction. And this is how you can also make a case if you have to show these results to somebody. You can visually just say, yeah, look, RM seems to be pretty important. Let's look into it. That could be something that we could work on if we want to reduce crime rates in a city, for instance. Any questions? Okay, let's move on then. Now, let's talk about a very interesting concept called bootstrap aggregating or bagging. So, growing one tree like we just did is nice, but it might still suffer from a high variance. The idea is that all the observations in one node will get the same prediction. So, we saw before that averaging always reduces variance, and we also saw that it doesn't affect the bias. So, averaging could be a way to lower the variance without touching the bias, so we might be able to improve further. So let's apply this concept here by growing trees, not one tree, and we can prune them, but we can use big B separate training sets. B stands for bootstrap or bagging. So how do we get B separate training sets? We could do something like cross-validation, where we divide our sample into 10 folds, sure. But if you want to take an average, don't take an average over 10 folds, take an average over 100. And in this case, dividing our sample into 100 subsamples might be an issue for the sample size. And this is where the bootstrap comes in. The bootstrap consists in resampling your training data with replacement. So, if I have a sample of 100 observations, I draw from this sample and I draw 100 observations. But every time I draw one, I keep it and I put it back, I put the value back in the pool. So it could be that sometimes I am taking an observation twice. It is possible. It is not a big problem. After all, if the data is continuously distributed, things can happen when you observe things discretely. So, resample your training data of the same size. So you get your original data and one sample of the same size that consists of a bunch of observations taken from the original bag. And then grow a tree on your new sample. Your new sample contains the observations of the first sample, but doesn't contain them in the same proportion. So once you grow a whole tree, it is going to be an entirely new tree. The cutoffs will probably not happen at the same threshold. And then you get another tree with a bunch of other nodes. So now what you can do is look at where one observation falls in one tree and in the other tree, and take the average of these two predictions, which themselves are already averages. If you repeat this b times, and typically b is like 100, 500, then you're going to get 100 different averages, which is an average of 100 predictions. So you take an average over 100 different predictions. When I say typically between 100 and 500, you can guess that this is another tuning parameter. How much should big B be? On one hand, you want it to be as big as possible. On the other hand, eventually your computer is going to take forever to grow that mini tree, prune them, and take the average. Rule of thumb is to take between 100 and 500. There is a moment after 500 where there is not a lot of changes anymore because we are taking so many averages already. But below 100, we can still improve by taking more averages. Now a quick word about bootstrapping. Bootstrapping is older than machine learning. It is an older concept that came around, especially back then, where data came in a very limited amount. When you have a small sample, let's say 50 observations or less, in the medical field sometimes you have as many as 20 observations, in biology as well. How do you make inference? How do you conduct hypothesis testing? It is a tricky question, because how do you test an hypothesis if you do not have a distribution to refer to? Remember that when we look at the OLS estimator, for instance, and we make hypothesis tests, we use the asymptotic distribution to conduct inference. So we use the distribution of the estimator when the sample size grows to infinity. But our sample is only equal to 50. So how good of an approximation this distribution is from the actual distribution of my estimator? If my sample is small, chances are my approximation is going to be very bad. So, Bootstrap was invented to circumvent that problem. If the asymptotic distribution approximation is suspicious or maybe not good enough because our sample is too small, then it's impossible to rely on it to make valid hypothesis tests and construct valid confidence intervals. The approximation error will be too big, and since you cannot quantify this approximation error, you do not know how wrong you are, but probably very wrong. So what you can do is resample. You have a tiny sample of 20 observations. Make a bunch of samples of 20 observations by picking from it. And every time, compute your estimator. Let's say beta hat. Then you would get 100 or 500 beta hats. Now that you have a bunch of beta hats, you can plot their distribution. It might look like a bell curve, but it might not look like a bell curve if it's a small sample size. At least you can use all of these plotted values to find the critical value for your hypothesis test. The bootstrap in theory also works better than asymptotic distributions in many cases. It is not the ultimate remedy to small samples, but it is an interesting alternative. Here, the bootstrap is used for a different purpose. The point is not to draw a distribution. The point is to be able to take averages of the predictions. The predictions themselves are averages. So we want to be able to take averages of averages to reduce the variance by not affecting the bias. So how do we implement this concept? Well, it's pretty much there. But once you grow not one tree, but 100 trees, and take the average of the predictions, then you should not call your model a regression tree, but maybe a forest. So, model averaging and bootstrapping together, I create new samples to be able to take more averages between my models. I can improve the predictive power of my trees. Random forest, take the average predictions of the B trees. The idea, to make a forest, you need many trees, hence the name. Now, it reduces the variance for the same bias, so we do not lose anything here, we do not sacrifice anything. But I want to talk about the random part of random forest. Why do I say random? You might think that's because I randomly resample my stuff. It is true that I resample in a random way, but this is not why the name random is here. The idea of random is that if you take the average of predictions, you're going to have a higher variance if the trees are correlated. If the trees are correlated, as in the splits are made over the same variables and over maybe the same cutoff values, or roughly the same, then once you take your average, you're going to take, for example, the average of two predictions. One prediction might be 10, the other prediction might be 10.2, because the trees, both trees produced pretty much the same structure, the same cutoffs. But taking the average between 10 and 10.2 is 10.1, which is pretty close to 10 and 10.2 in the first place. So averaging loses some of its bite, and your average will be close to the individual predictions of trees. So we're going to keep a high variance if the trees are too similar. And this is where the random part comes in. Every time we start a new tree, one bootstrap sample, one tree, I do not build a tree over all the possible x's. I'm going to randomly select a subset of these x's. So let's say I have 20 variables. On one tree, I can choose 5 variables. On another tree, I'm going to randomly select 5 other variables. Or they could be the same, but I'm going to randomly select. This way, the splits will not be made over the same variables and over the same values. So when I take the average, I will be able to decrease the variance of the trees even more. Hence the name random forest. same bias as one tree, but the variance is way lower. So the out-of-sample predictive power is going to get better. So if you have to use any form of regression trees, you can use a tree or two just to see how things look like, because visually one tree returns some interesting features. But at the end of the day, if you have to produce actual predictions, the best is to use a random forest. Of course, since you take the average of 100 trees, it's going to be hard to represent in one single tree. So you're going to lose the visual aspect. Although you could maybe make a tree where, well, you don't show really the nodes, the splits, but you just show the end nodes and say an observation in this will get that value and so on. But that would be more complicated. Let's compare. I use two models on the same data here. I have a random forest and a tree. I am going to plot the predictions of my two models against the actual data, the actual dependent variable. When you make such a plot, what you want to see ideally is observations, the points, the scatter plot, being centered around the 45-degree line. Because after all, you want your predictions to be close to the actual data. Now, you can see that the shapes are very different. Let's look at the tree first. If I grow one tree, what's going to happen is any prediction on my data, let's say here I have a bunch, 30, 20, 10, all the corresponding predictions of these points is going to be the same number, because all of these points ended up in the same leaf. So on the x-axis, they have the same x coordinate. Now, you could argue, you could see that here, those 2 points are very close to each other. The y is very close to each other in the data. But when I built my tree put this observation in a different node. And for this node, the prediction is the same for everybody in the node, which is something like 14. And this is why a tree predictions will have this kind of discrete aspect where there cannot be any value in between, because each value here corresponds to one node. So here, for instance, my tree has 1, 2, 3, 4, 5, 6, 7 nodes. Now, what happens if I use a random forest? If I use a random forest, I'm going to take the average of this point with the prediction from another tree, and another tree, and another tree, and so on. So the result is that the predictions will be very different for everybody, because if you build 100 different trees by selecting different covariates every time, the probability that two observations are always in the same node in each tree is pretty small. In such a case, these two observations will have the same prediction at the end. But as soon as one observation is in a different node on the next tree, then the average will be different and the prediction will be different. So the interesting feature of a random forest is that it introduces some kind of a continuity in the predictions, as opposed to a tree, which is either this, or that, or that, or that, or that, or that, or that. A random forest takes the average of these things over many, many trees. And this is what reduces the variance of the model. You can see, for instance, that the red points are more scattered around the 45-degree line, whereas the blue points are more centered, except for the outliers, but the outliers count for both, are there for both trees and random forest. If you had to fit a regression line through the blue points, the blue dots, it would be closer to a 45-degree line than if you did it through the red dots. Any questions? Okay, let's move on then. There is one last thing I want to talk about before we move on to the next main method. It's called boosting. Boosting is another way to improve the performance of trees. The idea is to grow a tree based on the previous tree. So we don't have to split the sample or do any form of bootstrapping. We use the same sample, but we grow trees sequentially. And each tree is going to be built upon what happened in the previous tree. Here's the algorithm. Start with a simple tree, really, 1 or 2 splits. That's it. You get your predictions, but your predictions are pretty vague because you have, let's say, 1/3 of the observations in one node, another third in the other node, and the last third in the last node. That's not very precise at this stage. That's underfitting. But get your estimates, get your predictions, y hat I, and compute the residuals, yi minus lambda y hat. Lambda here is a small value, so trees improve slowly. So the residual is going to be the difference between the actual data and a small number times the prediction. So at the beginning, your residual is going to be very close to your actual data because this will be very small. Then the next part is you grow another tree, but your y variable is now going to be your r. Your residual is going to be the dependent variable. And you repeat the same process. Once you're done, you compute the residual by taking this minus lambda times your new predictions. And you do this many, many times. Let's say p times. How to find p? You guessed it, cross-validation. P is telling you how many times you're going to grow a small tree. So the idea is to grow a tiny tree, just 2 branches. Okay? Then think about using those things as seeds for the next tree. And you grow another tree. Seeds for the next tree, and so on. Little by little, it turns out that your predictions are going to improve. They're going to get better and better and better. You lose interpretability here because each tree is going to be very small, just 1 or 2 splits. There's not much to interpret there. But your predictions will increase and get in performance and get as good as a random forest. And we do not need to resample. We just need to grow small trees based on what is left from the previous small tree. Boosting is used more generally. Imagine using this method on a linear model. You make a first regression with 2 variables, x1 and x2. You get the residual, and then you regress the residual on different variables. You get another residual, and so on and so forth. That could be a way to increase your predictive power. It is not as, it can be used, but I don't find it as appealing as a random forest. First, because I find it hard to understand what's going on in the background. Why does this algorithm increase the performances of your predictions? Whereas if you tell me about bagging or random forests, if you give me a graph like that, I can understand how the blue dots are doing a better job than the red dots, first of all. And I can understand how taking an average is always better for predicting than looking at one single value. So I found random forest better than boosting. That's why I don't talk about boosting a lot. I just, threw it out there just so that you know what's going on. You have a rough idea of what boosting is about. But if you think about regression tree, you should think about pruning to limit overfitting, and bagging, bootstrap aggregating, to reduce the variance while keeping the bias where it is. And finally, you should think about random forests. Let me finish this part with advantages and disadvantages of trees. First of all, as I said, it's visually appealing. It is easy to interpret. You can make a case, you can explain that to a high schooler. He will get that pretty quickly. If you have to explain to a high schooler how linear regression works, good luck. Some say they more closely represent human decision making than other types of regression. If you think about an OLS, you would never make such a computation in your mind. You will never think about, oh, I'm going to maximize and look for variance and covariance. Whereas trees, you could think, for instance, I have to predict the purchasing behavior of people at the grocery store. Well, you can already imagine that, for instance, who is buying? Is it a young person, an old person, a mom, a dad? That's the first split you could make in your mind. That might not be the most relevant one statistically speaking, but it will be some kind of relevant one way or another. And then you might think, okay, among women, you have the mothers and the non-mothers. Among men, you have the fathers and the non-fathers. And so on. And you can make like subsets of subsets of subsets, which is easier to represent in somebody's mind because it's not one fancy computation at once. It is one simple computation after the other, step by step, which is usually how the human mind functions. It's also one of the reasons I show algorithms so much. I don't want you to learn the algorithms by heart, but I want you to understand what is the process of building a tree. And if you show it step by step, it's easier than just making one long sentence to explain everything. Trees can handle qualitative covariates easily. We could make a split over male versus female, or over white versus any other ethnicity. It is clear and it's very easily interpretable. If you do a linear regression and you have many different qualitative covariates, you have to create many dummy variables. In fact, you have to create as many dummy variables as you have qualitative covariates minus 1. Just a side note. But that can be tedious to create a 1 or 0. If you're white, it's a 1. If you're not white, it's a 0. But if you're black, now it's a 1, and then if you're not black, it's a 0. That would be another variable. If you're Asian, you get a 1. If you're not Asian, you get a 0, and so on. Here, all of that is handled in a very straightforward way, the same way the algorithm handles quantitative variables. There are caveats, of course. There is no one best recipe in statistics, never. Trees don't feature the same level of predictive accuracy as other methods, like neural networks, which I'm going to get into in the next slide. And trees can be very non-robust. So if you make a small change in your data, in your training data, you could have maybe a value for a variable which is an outlier and you don't notice it. Your tree is going to be affected by that a lot. Why? Because a tree, in general, a tree is built based on averages. Remember that any outlier will always pull the average up or the average down. One of the reasons we do not care about average wage, but rather median wage, is because if you look at the average wage, it will look very big. If you look at the average wage in the data, it will look very big because there are a couple of people who are earning enormous amounts of money and they make the average very, very high, as opposed to using the median. The median is going to look at the value that separates the population into one half that earns less and one half that earns more. If you add a billionaire to the mix, that will not change the median a lot because you're just adding one person on one side. You go from 50% to 50.2%. So you just have to change the median a bit to make sure you go back to a 50-50 split. But if you add one billionaire to a small sample of wages, your average wage is going to get big. So trees are sensitive to such things. And as soon as we change the data a bit, the tree structures are going to change a lot as well. Note that this caveat is offset by bagging. By choosing another sample and doing this many times, we should be able to limit the influence of an outlier. Because in some samples we won't have it, in others we will. But at least we won't have them every time. And randomly selecting covariates is also a good way to limit that problem, because then sometimes I will not base my cutoff, my split, on extreme values, because I will not use that covariate, the one that features an extreme value, to make the split. I might use another value, another covariate, that doesn't feature any outlier. Alrighty, we've been at it for more than an hour, so it's probably time to take a break for you guys to let this whole tree business sink in. It's 3:45 right now. What do you say we get back to it in 10 minutes? 3:55? Enjoy your break. Okay, after talking about trees, regression trees in general, let's get into the other big machine learning tool for regressions called neural networks. In fact, it is probably bigger than regression trees because it is being used a lot for other problems than the ones we encounter in economics. You guys might have heard in the news or in some blog articles, or I don't know, some people talk about deep learning or neural networks. Those things are related to the notion of a neural network. So the idea is based on the structures of human brain's structure. We have neurons which are interconnected through some layers. But neurons are interconnected between each other, and here each layer contains multiple nodes, and nodes are connected to each other. I am not using the word node the same way I am talking about nodes when I talk about regression trees. Here a node is just pretty much a neuron. So in a regression setting, it consists in adding layers between yi and the xi's. And we regress yi not on the xi's, but on the layers of the xi's. So the idea is to introduce layers in between. I'm going to show you how we do that. And then regress y on these layers to improve or to increase flexibility of our model and to obtain a better predictive power. Imagine we have p different covariates. Define a linear combinations of the xi's that we're going to call zi as follows. So zi will be a linear combination of xi's, and each of these xi will receive a weight equal to alpha j. They are p different covariates labeled j from 1 to p, so they are going to be p alphas. Alpha 1 for x1, alpha 2 for x2, and so on until we get alpha p for xp. So far, that sounds a bit like principal components, but it is entirely different. The way we do it is different, and the purpose is also different. Now, consider P1 such combinations. So instead of making one zi as a linear combination of the xi's, we are going to make P1 zi's. And each of them will be a different linear combination. That's my layer. Now, because we want to increase flexibility, we are going to introduce a nonlinear transformation of my z's, because I do not want at the end of the day to estimate a linear model. Otherwise, if I put z in my regression, then regressing y on z is pretty much regressing y on x up to this linear combination, and OLS would do the trick. Here we want to increase flexibility, so we introduce a nonlinear transformation, g, that could take many different forms. I only give you one example here. This function, 1 over 1 plus exp minus z, has the interesting feature of being very flexible. So first, create the z's as a linear combination, but this gives you one single number, and then do 1 over 1 plus exponential of minus that number. You're going to do this for each variable z that I labeled k, and k goes from 1 to p1. And finally, you estimate the demand model, the following model, where you put y, but x is not in there anymore. You regress y on the combination of these j. So if you have p1 different z's, then it's going to be beta 1 g of z1 plus beta 2 g of z2 plus beta 3 g of z3, and so on, until we get to beta p1 g of z p1. So x is embedded inside the g. It's embedded inside z, which is embedded in turn inside g. So we are adding layers of functions on top of my x. This way, we are increasing the flexibility, and now we allow for all kinds of wavy patterns instead of just a straight line. Note here that beta k, yes, show up, all the beta k's show up linearly. So if we only care about estimating beta k, then sure, we can use OLS. However, to build the z, we have to find what the alphas are. So part of the minimization problem will be to also find the alpha jk. And since the alpha jk do not show up linearly because of the function g, then now we are getting into the realm of non-linear least squares. So if I replace z by the function that I made before, then what I am actually estimating as a function of x is yi equals the sum of beta k's, g, and g is a function of this linear combination. But remember that this linear combination gives you one single number. And then you just apply g on it. And then that's what you throw in your regression. That's what you want to estimate. So because alpha doesn't appear linearly anymore, it is not a linear model, so we cannot use the easy commands in R. We gotta get into the fancy packages. And the estimates alpha hats and beta hats will not follow the same formula as the OLS formulas, precisely because beta and alpha, because alpha in particular doesn't show up linearly. There won't be a closed form solution for alpha hats and beta hats. So this is not something that we could compute by hand. If I give you 10 observations, you can in principle find the estimates of beta 0 and beta 1 hat in an OLS estimation. Just find the variance, find the covariance, and plug the numbers. Here, there is no closed form solution, so the computer is going to iteratively go over different values, and in an educated way, of course, we'll go from one value to the other, hoping to decrease the objective function further. And once it has reached a minimum, the computer will say, if I change the values, now my objective function is higher. So I'm done. Where I am is a good spot. I am at a minimum. In general, we call this a local minimum because it's not always possible to find the minimum of all the different minimas. Sometimes the minimum, the function could be like this, so there are multiple minima, and sometimes the algorithm can be stuck into a local minimum, which might not be the smallest minimum. We call this a neural network or model, with a single hidden layer, the Zs, with P1 nodes, because we made one layer of Zs and we used P1 Zs. Now, you can imagine that if we call this a single hidden layer, is because in general, we don't use a single layer. We use way more. We use 4 or 5 layers. And you can see how it gets messy very quickly. So I'm going to give you an example with the simplest numbers I can find to give you an idea of the model that the software will estimate for you. Imagine we have 2 x's, x1 and x2, and we want to add one hidden layer using 3 nodes. So we want to construct 3 z's, and each z is a linear combination of the 2 x's. So first of all, we build the z's. Linear combination of the x's. So z1 for node number 1 is going to be alpha 1 1 x1 plus alpha 1 2 x2. The second subscript corresponds to the corresponding x, and the first subscript corresponds to which node we are looking at. Zi2, node number 2, will then have coefficients alpha 21 x1 plus alpha 22 x2. And finally, Z3 will have its own alphas, alpha 31 x1 plus alpha 32 x2. Those numbers are different. They are different from each other. So we create new variables every time. So far, how many alphas are we estimating? Well, 6 of them. 2 per node. So this 2 per node. So 2 times 3. That makes 6. But now, the main regression is yi as a function of beta 1 g of z, 1, plus beta 2 g of z2, plus beta 3 g of z3, and of course, the infamous epsilon, the infamous error term. So in total, how many parameters do we want to estimate? We have 6 alphas because we have 3 nodes containing 2 x's each, and then we regress y on each of the nodes, and each of the nodes gets a number in front of it. So we have 3 additional parameters. So 2 times 3 plus 3. That's 6 plus 3, 9 parameters. Just with the small numbers, we already have 9 parameters to estimate. You can imagine the mess when you make 2 hidden layers with 20 x's. So 2 variables, 1 layer with 3 nodes makes 6 parameters to estimate inside the g functions, plus 3 from the number of nodes, 9. It is common to add multiple layers. So now imagine that each z is a linear, imagine that we make a new variable w, which is a linear combination of the z's, which itself is a linear combination of the x's. And that increases the depth of the neural network. This is why you hear the word deep learning or deep neural networks pretty often. The depth, same as a tree, corresponds to the complexity of the model, of either the network or the tree. Imagine we had another layer of 4 nodes. Then we have 2 x's times 3 nodes, because we have 3 z's. But then we have we're going to have 4 different additional nodes. So that makes 24 parameters to estimate just inside the brackets. And then at the end of the day, you're going to regress y on g of these w's. And since we have 4 w's, then we have to add 4 more w's to this number. 24 plus 4, and we get 28. It might seem like a big problem when it comes to finding all these coefficients, because at the end of the day we have function inside a function of a linear combination times, well, where the function is 1 over 1 plus exponential. Seems like a mess. Computers can handle those tasks nowadays relatively well. But there are still some research around optimizing these functions. There are many different ways to minimize a function in a software. Some of them are analytical. They actually compute the derivative and set it equal to 0, the same way we would do that in ECON 201 or ECON 302. Others are going numerically. They start with a certain value. They look at how big the criterion function is, and then they have some steps to get to the next best value, and they get to the next best value, and so on and so forth. And once they do not find a next best value anymore, then they have reached a solution. Note that I say a solution, because if there are multiple minima, then the software could be stuck in a minimum that we don't really care about. We want the best of the minima. We want the minimum of the minima. It's a fascinating topic outside of the scope of this course, but it's really, really interesting. It's called numerical optimization. You can take a look on Wikipedia on how computers get it done. It is fascinating. More layers increase the flexibility and hence produce better predictions. Choosing the depth of the neural network is another tuning parameter. How many layers do I want to add? Why 3 nodes? Why 3 Zs and not 5 Zs? And so on. So these parameters have to be also found. They can be some kind of penalty term on the regression function, same as some kind of a lasso, where we do not want to have too many parameters either, otherwise we will get into overfitting. But neural networks are used a lot and way more in other areas than in economics. In economics, pretty much what we are looking at here is a highly nonlinear function. We already have tools for that. Neural networks are convenient to handle big data where more flexibility is needed. In economics problems, we do not deal with big data very often. We might deal with big sample sizes, but we don't deal with thousands and tens of thousands of variables, of x's. In general, we might have we might have 100, that's already a lot of x's. Plus, you don't get any interpretation for your coefficients here. If you want to look at the marginal effect of x on y, as in you increase x by 1 unit and see what the increase on y is, then you would have to take all of these derivatives by hand, but that totally defies the purpose of such a method. The point of this method is to be complex. So you do not want to get into find a simple estimation, because precisely you want to get away from simple. You want to add flexibility. Facial recognition, voice recognition, speech recognition, words recognition on documents are programmed with some form of neural networks. They apply in different ways, but in general, they are based on the same idea. The idea is that you feed the algorithm a bunch of x's, that could be letters or a bunch of voices, sounds, and then using all of these layers in the middle, well, those sounds are coded. For instance, letters will have a name. For example, letters will have a number associated to them. And for voices, I'm not exactly sure how it's being recorded. It could be some sort of a frequency or something like that. But a numerical value is obtained for these inputs. That's what they call them. For picture recognitions, they use pixels. Each pixel, a picture is divided into pixels, and each pixel corresponds to a numerical value. So a pixel where half of it is red, the other one is blue, will have a different value than a pixel which is entirely blue. They're going to use all of these different values as inputs, create layers, and come out with an output that is going to tell them, oh, that's what it is. I recognize this voice, or I recognize this word, and so on. So neural networks are used extensively in the machine learning literature due to their flexibility and predictive power. Facial recognition, picture identification. You know the famous quote, is it a bird? Is it a plane? No, wait. I know what it is. I have an algorithm for that. I strongly suggest you to look at these two links. They will point you to, I think, blogs that talk about how neural networks are used for facial recognition, but in very layman's terms, very general terms. I missed, there was a link to a blog at some point where the blog explains how picture recognition works in very detail, so I would not be able to follow everything. But what they had that was interesting is, at the front of the website, they had a picture, let's say of a bird, and it says what the algorithm is predicting. It says no, not a bird, or it says it predicts a dog. And then as you click pass, 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 and you show more pictures to the algorithm starts to get better and better. And by the time you click to the 50th picture, the computer is 90 or 95% of the time accurate and tells you it's a bird when the picture is actually a bird. The interesting thing about this blog is that those pictures are randomly, not generated, but randomly picked on the web. So those are not pictures that the algorithm has seen before and stored in its hard drive or something, in its memory. It's based on the first pictures that he saw and where he got very, very wrong. Eventually, he recognized some patterns using the pixels, and eventually was able to predict, that's a dog, over that's a bird, and so on. I missed the website. I forgot where I found it, so I could not put it here, but it's a very interesting thing to look at. And fancier versions are coming out on a regular basis. And so do easy implementations on statistical software across the board. R, MATLAB, Stata, Python, C, Julia, and other statistical languages that I have no idea about have packages that implement neural networks. If you see an ad on LinkedIn that talks about using deep learning or PyTorch or words like this, where they pretty much talk about neural networks, they pretty much ask you if you know how to use a specific package in order to produce predictions. Personally, I don't know them because I don't know all the statistical languages they require, but I, and now you, know the principle. So if you do a bit of programming, you can learn any language fast enough and then learn how to implement neural networks. This will open a lot of job opportunities to you guys. So if you can, mention that you know a bit of programming, mention that you have the basics of machine learning. You can show it or rehearse it, read more about it at home. The principle is never really hard. In fact, I had a very hard time finding videos online that talk about neural networks in a mathematical way, in a statistical way. They will all show you the picture of the layers and the nodes, and they say, oh yeah, we create layers and interconnected nodes. I was like, yes, I understand that, but what does a computer do? The computer is not creating nodes for funsies and making a plot. You need to give numbers to a computer. And I found that many tutorials are not very explicit about that. Try to open the black box. Try to understand what is being done. Same with regression trees, in fact. You can find textbooks that explain this very well, but you can find many videos where they're very general about, oh yeah, here is a tree, we make these predictions, and that's how it works. But they don't tell you exactly what's going on. If you know what's going on, that will open many doors for your future career. Any questions? Okay, so I'm pretty much done with regression problems, but we are still talking about supervised learning. We still have a wide variable of interest that we want to predict. However, it is not quantitative anymore, it is now qualitative. This is what we call classification problems. We want to classify an observation as being either 1 or 0, a yes or a no, a blue, a green, or a red. So, regression makes sense when y is a quantitative variable. But if the dependent variable is qualitative, marital status, smoking status, choice of a product, choice of a brand, the interpretation of a regression is a bit different. And prediction in this case is about whether an observation is likely to take one option or another. Based on some characteristics, I predict that this consumer will buy this brand or will not buy this brand. Or I predict that this couple will divorce within 1 year based on their history. That's also something that is being done. And in fact, predictions are pretty good. People might think that the relationship is unique, that it cannot be summarized by algorithms and so on. Turns out that predictive power can be very, very good. Of course, you might be one of these where the algorithm is failing at predicting your status, but for many others, predictions can be pretty accurate. For this part, for classification problems, when we talk about different options, like yes, no, smoker, non-smoker, single, divorced, widowed, red, blue, green, we talk about these values as classes. And so we want to predict a class for an observation. We would like to pretty much predict the probability that y would be equal to k, where k is a class, given what we observe for that observation, given all the x's we observe from that observation. Two classes could be yes or no. Three classes could be bus, car, and bike, if you are interested in making a study on the choice of transportation. So let me quickly go through linear regression and what we call logistic regression. Why quickly? Because, well, it's not really part of the machine learning algorithms. And second, because it's not, the linear regression at least is not really relevant for these problems. Why not perform a linear regression? After all, linear regression is about finding causal patterns and using correlations between the x's and y. Well, imagine the sign of a beta hat. The sign of the coefficient will tell the effect on the probability of y being one class or another. For instance, if beta hat is positive, it might tell you that increasing the corresponding x will increase the probability of y be equal to one option. However, regressions might be able to produce predictions that exceed 1. If y is only equal to 0 or 1, as in yes or no, how do you interpret a prediction of y which is bigger than 1? Or sometimes smaller than 0? So it is harder to interpret, although the general intuition remains. A positive beta hat will have a positive impact on the probability of y being equal to one class. But by how much this probability will increase, it is harder to quantify, especially because it might exceed 1 or go below 0. Another approach, which is still called regression, is to make an assumption about the distribution of the error term. If we make an assumption about the distribution of the error term, then we can compute the probability of the error term taking one value or another, right? But if you write the linear model as y equals xi prime beta plus epsilon, then it is the same as saying that epsilon is equal to y minus xi prime beta. If you know the distribution of epsilon, then you know the distribution of y minus xi prime beta. And you can use this probability to estimate the coefficients. And in particular, a very important distribution is called the logistic distribution that says that if x follows a logistic distribution, the probability that x is lower or equal to small x is equal to 1 over 1 plus exponential of minus x. That should ring a bell. We just saw this function in neural networks. This function is particularly nice because it is very flexible. If you use polynomials, if you want to obtain flexibility from polynomials, you need to have power of 4, 5, 6, 7. You need to include powers of x. With just this function, you can obtain very wavy functions, very wavy curves, which is why it is also used in neural networks. Note that indeed this is a probability because it is not bigger than 1 and not smaller than 0. An exponential is always positive, so 1 plus exponential is bigger than 1, and 1 over this will be smaller than 1, or bigger than 0. And so if you want to estimate the probability of y being equal to a certain class, then you have to estimate this model using what we call maximum likelihood. This is not something I talk about in this course, but it is one of the big building blocks of econometrics. I talked about parametric models in the first lecture. Maximum likelihood estimators come from parametric models because we need to fully specify the distribution of the variables. It is a very interesting estimator that has very interesting properties. I suggest you to maybe look at it online or in the textbook, but this is not something I want to talk about in this course. Rather, let's make trees. Think about the previous regression trees, but now the variable y belongs to a class. 1 for yes, 0 for no, or 1 for option 1, 2 for option 2, and so on and so forth. The idea of the tree is to predict someone's decision based on his characteristics, based on where the observation falls at the end of your tree. For instance, think about predict purchasing behavior based on browsing history. Amazon, for instance, has access to your browsing history, the time you spent on each page, what you clicked on the page, and so on. And based on that, they will predict your probability of buying a certain product. And based on that, they will probably suggest you to click on the product again and again. The algorithm is the same as regression trees. In fact, we can use pruning, we can use bagging, we can make random forest, we can use boosting. No problem with that. We already know how to do it. However, one thing needs to change. Think about the sum of square residuals. Here, in the case of classification, y is only equal to 1 or 0 or 1, 2, 3, and so on. It is not a continuous variable. So we don't really care about getting as close as possible to 1. Because if our prediction is 0.9, what do we do with that? Do we take this as 90%? Do we take this as it's closer to 1 than it is from 0? So we need to design a different objective function to minimize when we make our splits. Imagine that p hat mk is the proportion of observations from class k in leaf m. Remember, we have many leaves at the end, terminal nodes, and we have observations that have different classes in each. P hat mk is the proportion of the observations that are from class k. The idea is that we want to predict somebody's behavior. We want to predict a class for somebody based on where his observation falls in the leaves. If a leaf has 50-50, 50% of yeses and 50% of nos, how do you predict what do you predict? Now, the prediction for an individual in leaf M will be the class that is the most occurring. So if you have 70% of yeses in a leaf and 30% of no's, then anybody who ends up in this leaf will have an estimate, will predict his the probability of him getting a class. Well, we'll predict that he will take the class of that is the most observed in the leaf. So we don't predict it's going to be a 70% probability. No. We predict that somebody who falls in this leaf, because the majority is a yes, this person will go with a yes. That's our prediction. Now we need to find a way to make the splits optimally. So there are different criteria which are very different from residual sum of squares. The first one is called entropy. It is used in statistics. I believe it's used in physics as well, but I don't really know much about it beyond statistics. Let's look at it. Minus the sum over all the classes of the proportion of people in class K in leaf M times the log of that proportion. So first of all, if p hat is a proportion, it's between 0 and 1. So this is positive, it's between 0 and 1. But the log of something between 0 and 1 will be negative. So this whole thing here will be negative. If you sum it up, it is negative again. But since we put a minus in front of it, our criterion will always be positive. So this is a criterion we want to minimize. Another criterion, which is similar, is called the Gini index. Instead of looking at the log, which turns this thing into a negative number, we look at 1 minus p hat. Because p hat is between 0 and 1, 1 minus p hat will be between 0 and 1, positive. P hat is positive, and so this whole thing here is also positive. So both criteria are positive or they are zeros. Imagine that p hat is equal to 1. So imagine that in one leaf, everybody is a yes. Well, p hat will be equal to 1. Log of 1 is equal to 0. So this whole thing will be 0. Here, p hat is equal to 1. 1 minus 1 is equal to 0. And again, the whole thing is equal to 0. Now imagine that p hat instead is equal to 0. You are in a leaf where nobody is a yes. Then p hat is 0. The whole thing is 0. And here as well. Well, in fact, what am I saying? Can they be 0? Probably not. Sorry, I just realized. They can be close to 0, but since you take the sum over all the k's, the probability must be bigger than 0, the proportion must be bigger than 0 for at least one class. If there are no yeses in a leaf, there must be some no's. But when p hat is close to 0 or close to 1, all of them, both criteria will be close to 0. And so, the more pure a node is, and by pure we mean the more it contains people with the same class, the lower the criteria. So, classification trees minimize one of these criteria at each split. The idea is that we don't want to have leaves with a bit of yeses and no's in each. We want to predict who is a yes and who is a no. So at the end of the day, we want to get leaves where we have straight yeses and straight nos. This is what's important. This is why we use these criteria. We want to be able to tell firmly, I predict this person to be a yes because he is in the leaf where everybody else's is a yes. If a leaf has 50% of each, a prediction will be very difficult to make. Here is an example in R. So here is another data set. I forgot it's a healthcare data set that is trying to predict the probability of dying or surviving based on some data. First of all, first node, we have 100% of the observations. 38% of them survived, which means that the majority here is people who died. So the first prediction here is, well, based on my sample, the majority died. Then I make my first split. The first split is going to be optimal regarding the gender variable, male versus not. If observations are male, they are being put into that category. And then no need for a further split. And it seems that the prediction for male is to be a survivor because 73% of the observations were survivors. This node corresponds to 36% of the total observations and 64 among the ones who died. So this tree is first looking at who is a male, who is a female, and is predicting that any male will be a survivor. Then among the females, more splits need to be done before saying who survived and who died. Age seems to be another factor. If age is bigger than 9.5 years, then the prediction for women aged older than 9.5 years is that they died. Because only 17% of that part of the sample survived. Note that out of the 64% of observations, 61% end up in this node. Then the algorithm predicts that the next proportion survived because 53%, it's a majority, not a big majority, but it is a majority, survived. That represents 4% of the observations. I guess 3, but that's a round off. And then another split is being done using this variable, which I believe is connected to siblings. Women older than 9.5 with this variable bigger or equal to 3 are predicted to die. They represent 2% of the sample because only 5% in that node survived. So a crushing majority, 95% of observations in that node died versus the ones who survived, which is a crushing majority here. Note that the same tree can be done with multiple classes. Every time you just look at the majority. The majority is blue, so the prediction for this observation is going to be a blue. But the other one could be red, or the other one could be green, and so on. Any questions? Okay, so far so good. then let's talk about support vector machines. Support vector machines are another way to conduct classification. The idea is to cut the data with hyperplanes. So you plot your scatter plot, you get your scatter plot of data, and the idea is to find a line to cut your data into the ones which are predicted to be a yes and the ones which are predicted to be a no. Of course, there are a lot of subtleties. First of all, what is a hyperplane? In mathematics, a hyperplane, when we talk about a p-dimensional space, is an affine or a linear, same thing as linear, subspace of dimension p minus 1. Fancy. It's actually easier than it sounds. Imagine you have a two-dimensional space. It's a surface. Imagine you have your graph. Oops, here. Length and height. And you point somewhere as an x and a y. 2 dimensions, one x and one y. A hyperplane will be then an object of dimension less than 2. So 2 minus 1 is equal to 1. An object of dimension 1 is a straight line, only the length. There is no height. So a hyperplane will be a line that cuts your surface into 2 halves. It's as simple as that. Imagine you cut a piece of paper with your scissors. Your scissors will go along a hyperplane. If instead you are looking at a 3-dimensional space, so you have a height, a length, a height, and a depth, 3 dimensions, you have a z, then a hyperplane will be a 2-dimensional space. It will be a flat wall, a surface, that is going to cut the space into 2 halves. For instance, the window which is in front of me is a hyperplane. It is cutting the whole space into 2 halves. The half where I am, inside, and the other half outside. So, we want to cut the data so that each plane contains one class. And then you just need to find where a new observation falls, in which half space, and you can give him the corresponding prediction, the corresponding class as a prediction. Fairly straightforward, right? Now, how do you choose the best hyperplane? Let's say this one cuts the data. If this one can cut the data, then this one can do it too. This one can do it too. This one can do it too. And you can see that as soon as you can fit a hyperplane, you can fit an infinity of them. Which one should you pick? We want a hyperplane which is as far as possible from any observation. Why? Because it will make it clear that whenever there's a new observation, whichever side it falls on, the prediction will be clear. So the idea is to compute the perpendicular distance between the point and the potential hyperplane. Like this. You look at this distance. You want to maximize this distance. You want to make sure that your hyperplane is far from observations in general, because it will make a clear cut on where observations fall. If a point is very close to the hyperplane, it means that it could have rather gone to the other side. But if it goes a tiny bit on the side, then it changes class. And that's something we want to avoid. We want to have a clear way to classify observations. The smallest of these distances is what we call the margin. What we want to do is maximize the margin. We want to maximize the distance from the closest point. Let that sink in for a bit. This is what we call the maximal margin classifier. The vector that represents the distance between the hyperplane and the margin is what we call the support vector. This is the vector we used to find the location of our hyperplane. Many observations were not used to find the boundary, because observations which are very far from the boundary will not affect the boundary. The boundary is affected by the ones which are close. And the ones which are used to find the optimal boundary is the one we call the support vector. And sometimes there are more than one support vectors. Now, I'm going to show you an example, but when you make a scatter plot over 2 dimensions, to make things simple, you have a bunch of points. Some points have a y equal to yes, some points have a y equal to no. You want to find a plane, a hyperplane, that separates the data into 1/2 full of yeses and 1/2 full of no's. Is it always doable? No. Sometimes you could have a bunch of yeses and in the middle there is a no. How do you separate the no from the yeses? With a straight line, it will not be possible. So, we want to also allow for this kind of slack. So instead of using what we call a hard margin, where strictly yeses on one side, no's on the other, we can use a soft margin. So we allow some observations to cross the border, cross the boundary. That's the best thing we can do. If we have a majority of yeses on one side and another majority of no's on the other, at least we are able to classify a lot of observations, but maybe 1 or 2 are on the edge. So the minimization problem is modified by introducing slack variable. We allow some errors in some observations being on the wrong side of the fence. I'll show you how this looks in a graph in the next slide. Now, I gave you an example where we could have 1 no in the middle of a bunch of yeses. Is it good to make a straight line then to separate observations? Probably not. If the no is right in the middle, then maybe it should be part of the same plane, or maybe we should isolate the no's among the yeses. And that's why sometimes boundaries are better not being linear. For instance, you could include a polynomial of the covariates of the x's. So instead of looking for a straight line, so our minimization problem is linear, then we can include some squares, some cubes, and so on to allow the boundary to be more flexible. And this is the extension of that method that we refer to as support vector machine. So the problem of maximization of the margin needs to include other measures of similarity between observations. Observations are not similar just in terms of where they fall or how far they are from the boundary, as in straight distance, but you could allow for other measures of distances rather than just a straight line. There is a function, or there are some functions, because there are many of them, called kernels, which means, kernel, which are functions that quantify such similarity differently. A linear kernel, for instance, will look at straight distance between a point and the boundary. But other kernels can include other ways to look at a distance. In particular, we can include curvature. And using a different kernel will produce different boundaries. And they are fancy. The formulas are fancy, so I won't show any here. Let's get to an illustration in R. I have x1 and x2 here. So I have a variable y, which is binary, is equal to yes or no, 0, 1, minus 101, 102, doesn't matter. And each class is represented in a different color and a different shape. So blue triangles are, let's say, a yes, and red circles are, let's say, a no. And if I plot my points on the x1, x2 plane, then this is what I get. A support vector machine, a regular linear boundary, would look for a way to separate the observations in a way that one side only has blue triangles and the other side only has red circles. You could think about something like a boundary of this kind. Seems to work. But I say seems because we have this blue triangle here, which is annoying. If I separate my plane, my surface here, then my blue triangle is on the wrong side of the fence. And that will be an issue. If I run my algorithm, I find some sort of a linear boundary that is still going to include maybe the wrong point on the wrong side, because I am including a soft margin. Now here the variable happens to be either -1 or 1, which is why all the observations that would fall in the red area would be classified as a 1. All the ones that would end up in the yellowish, the beige area would be classified as a -1. Now, that would be the basic one, but you can see that I don't have many data points. So yes, this one will be included, will be on the wrong side of the fence, sure, but it's not a big deal, right? But if I have 10 times as many points, then it's gonna get messy. I'm gonna have blue triangles on the left, red circles on the right, and so I will have to be more careful about how I want to trace the boundaries. So imagine we have such a scatter plot where we have many blue triangles in the middle, and overall we have red circles on the extremes. Well, here a straight line will not do. Wherever you use a straight line, you're going to include a bunch of either class on each side, and so you won't be able to predict much. This is where we are going to use nonlinear boundaries. The same observations are now here, and you can see here that there is a gradient being given, so that depending on where observations are falling, we give them a straight classification, like a straight yes or a straight no. But if they fall in, let's say, the white area here, the algorithm gives them a meh classification. Hard to determine where they're gonna fall. Note that since we see many blue triangles in the middle, the algorithm picked that up by making a blue area here, and the darker the blue, the more straight the prediction. So if you have a blue triangle here right in the middle, the prediction is definitely a blue triangle. The prediction is definitely going to be the same class. But if you're close to the boundary, let's say here, where you are outside of the big turf of red circles and not yet inside the turf of blue triangles, then the probability is, the prediction is less clear. Any questions? Support vector machines are not used so much in economics because we have other tools for classification that do also a reasonable job. But they are used in many other areas, and there has been a lot of research on how to figure out these non-linear boundaries and what to do with the ones at the corner, at the edge. So I showed you two different functions in R. This one is nice because it shows you the gradient of definite, that's the class, and not so sure. We are in between two different, we are close to the boundary, so not so sure. Whereas the first graph is more straightforward. Any point that falls in the red area, as close as to the boundary as it may be, will get a value of 1 as a prediction. And any point that lands in the beige area will get a prediction of -1. How do we deal with multiple classes now? Trees are pretty good for that. We saw that we can just keep building trees and look at the majority of one class in each leaf to build a prediction. How do we apply support vector machine when there are more than two classes? The extension is not straightforward, and I'm just going to briefly talk about it. The two most popular approaches are the 1 versus 1, where we make many different SVMs, but every time we compare two classes, 1 versus 1. So if I have green, blue, and red, I'm going to make an SVM for green versus blue, blue versus red, and green versus red. I'll have 3 different plots like the previous one, and then I will assign an observation to the class it was assigned the most often in each of the comparisons. For instance, if it was blue versus red, it was classified as blue, and blue versus green, it was classified as blue, then the prediction will be blue. That's the 1 versus 1. Make many different SVMs and see where the observation falls every time. Choose the class where the observation falls the majority of times. The other one is the 1 versus all. You fit a support vector machine for each class versus all the other class. So you turn this into a 2 classes problem. If you have red, blue, and green, now you do red versus not red. And so the blue and the green will be classified as not red. Then you do the same for blue versus not blue. That's a second SVM. And then you do the same for green versus not green. Finally, you assign the test observation to the class where its distance from the boundary is the largest. There are also more sophisticated ways, but these ones are the most straightforward ones because you just have to make an SVM. For each class using 2 classes every time. Okay. How is everybody doing so far? Any questions before I talk about the last part of machine learning methods? Yeah, there is a lot to unpack, so you're gonna have to read things more, maybe watch the video again. There are a lot of terms. You will need to know a lot of them for the final exam, which is sure in a long time, but try to at least understand the gist of what I'm explaining, and then you can review the technical details later. So, let's finally get into unsupervised learning. Supervised learning, what we've been doing so far, is well understood because we have a way to check the validity of our methods. thanks to the dependent variable. So we can use the variable y to check if our predictions are good. And so in this sense, we are supervised. We have a way to check we are in the right direction. We have a way to check that we are overfitting as well. Unsupervised learning is more tricky. How can you check if you're on the right path if you have no ways to compare your work on actual data? In this sense, we are not supervised. So we have to thread more carefully, but they are methods. Often we use unsupervised learning as a way to analyze data before getting into any sort of predictions, regressions, estimations, and so on. We usually use those tools as a way to observe patterns in the data, something such as correlations, similarities, and so on. Remember, with unsupervised learning, we do not have a y, we only have a bunch of x's. So if you do have a y, you can still do this step of looking at the x's and see if there is any trend or pattern before getting into regression problems or supervised problems. If you don't have y, the point is to find those patterns, draw correlations between the variables in order to, in general, separate observations and put them into different groups according to some covariates for later purposes. Here, we will go over two different methods. Principal component analysis, which you already know. It's a way to visualize high-dimensional data using a low-dimensional representation containing as much variation as possible. And the second is called clustering. The idea is to create groups of observations based on some similarity measure. So let's get into PCA first. We generally use it to observe high-dimensional data before getting into further analysis. In the model selection lecture, we also saw that we can use it to reduce the dimension of our x's while keeping the main features, which are variance, covariance, and correlation. It summarizes the variance and the correlation patterns of covariates in a more compact way by reducing the dimension while keeping the important features. So we look for m variables, which is way lower than the p original variables at hand. Those variables are linear transformation of the x's. Each of these variables is going to be called a principal component. So if I have m principal components, I'll have big M z's. Each z is a linear combination of my p x's. So I might have many x's, but since I am summing them, I obtain only one single number. And the point is that my z's can be analyzed and contain the same patterns as my x's without dealing with such a high-dimensional data. Here is the idea. First, standardize each variable so they all have mean 0 and standard deviation 1. The idea is that PCA is sensitive to scaling. So if one variable has a way bigger average or a way bigger standard deviation than another, that will have a big impact on the results of the analysis, and not in a good way. It will hide some patterns or it will exaggerate others. PCA finds the coefficients to maximize the variance of the z's. So the idea is that we want the z's to have the same variance as the x's, but we have way less of them. So we want the combinations of x's to feature as high of a variance as possible. And we are going to look for the phi's, the coefficients, that maximize that variance. once we have one principal component, let's say Z1, then we're going to have Z11, Z12 for each observation. Each observation of Z1 is what we call the score of the first principal component. We are looking at Z1, each observation of Z1. This is why we call them the scores. That's how you do to find the first principal component. Then you repeat the same process to find Z2. But in the process, you want to make Z2 have maximal variance and be uncorrelated with Z1. And you repeat the same process until you get to your last Z big M, not small m. This process is best explained graphically. So first, imagine you have some data on crimes in each state of the US. So there are 50-ish observations. I forgot if it's 51 or 52 here. And each observation is a state that has crime statistics for different categories like rape, assault, murder, and some other related characteristics like urban population and so on. In fact, here we only have 4. If you do a principal component analysis, you are going to get here 4 principal components. M here is then equal to 4. The idea is that since P is equal to 4, big M cannot be bigger than P. Now, since we process sequentially when we compute our principal components, well, the computer does everything at once, but we can do it sequentially. Let's look at PC1. PC1 has the highest standard deviation, the highest variance. So it's a new variable with the highest variance among the 4. And also, it has the highest proportion of the variance. 62% of the variance in all the x's is explained by just the first principal component. The second component has a way lower standard deviation and represents 24.74% of the total variance in the x's. If you cumulate 0.6201 and 0.2474, you get 0.8675, which is just the first 2 principal components. Together, this is how much variation they explain, how much variance of the x's they explain. If you add a third component, which only represents about 9% of the total variance, the cumulated variance is 95%. Finally, because we cannot have more components than the number of variables, once you get to the fourth, the proportional variance is very small, but when you add all of them together, you get to the total variance of the x's. Now here, we are representing four variables with 4 components. This is not the goal of PCA. The goal of PCA is to represent 30 variables with 5, or 1,000 variables with 50. So in general, we usually cut components at a portion where we deemed that the explained variance is good enough. For instance, here if I look at my 62%, is this good enough to explain the variance of the x's? Not quite. It's barely more than the average. Barely more than half. So let's add a second one. Ooh, now we're talking. 86% of the variance. That's just with 2. So that starts to be a pretty good number. But then, as soon as I add a third component, I have a 95%. That could be a good cutoff. Because at the end of the day, I do not want to represent 4 variables by 4 other variables. I want to represent 4 variables with less variables. So where to cut is always a topic for debate. Because the problem is unsupervised, cross-validation will not do here. You do not have a way to compare this to any sort of data. You can only say, well, that's 95% of the variance. Is this good enough? You have to figure that out. Now, graphically, here is what it looks like. Here, we plotted all the observations on the two first components, on the two z's. Remember that z has no interpretation per se. Principal component is a linear combination of rape, assault, murder, and urban population. It doesn't have any interpretation in itself. Now, here we plotted each data point according to, well, their coordinates regarding the principal components. And note that these vectors, murder, assault, rape, and urban population, are going to indicate a lot of things. So let's get into it. So first of all, PCA is a convenient tool to see what variables are correlated and feature the most variance when many covariates are available. Think about big data. How to choose the number of components? As I said, no systematic way. If the first three components add up to 90% of the explained variance, that could be deemed good enough. It's up to you. Now, let's look at the graph. Note that these three vectors are relatively close to each other, whereas the last one seems to go in a very opposite direction. How close these vectors are tells us how correlated these variables are. So murder, assault, and rape seem to be positively correlated because they go in the same direction and they're pretty close to each other. Now, the magnitude of these vectors is relatively the same, so they also feature a very similar variance. Urban population, however, is a bigger vector and it's further away from these three. So it's less correlated with those crime rates and it features a higher variance. Now, how do we interpret all these states on the plot? So, first of all, you need to compare the direction of a vector and where the point is, where a given point is located. For instance, if you look at rape going this direction, then it suggests that Nevada, California, Arizona, Illinois, and so on have relatively high rape rates, as opposed to West Virginia, Vermont, and so on. And you can do the same for the other variables. Mississippi, North Carolina, and South Carolina are or have a rather low urban population because those points are located at the opposite of the urban population vector. Now let's talk about the coordinates. Urban population, for instance, has a negative coordinate for PC1 and a negative coordinate for PC2 as well. Now note that in terms of magnitude, along the PC1 axis, this vector has a small x. It's close to 0. On the other hand, murder, assault, and rape are close to between -1 and -2, so they have a higher magnitude. This means that murder, assault, and rape were used more when making PC1, when making Z1, than urban population. However, you can see that urban population in terms of y-axis goes way lower than all the other variables, which are between -1 and 1. This one is lower than -2. That means that the second principal component, Z2, used mostly urban population as its main variable. The weight on that variable was higher than the weight on murder, assault, and rape. This graph is looking at the relationship between 4 variables on a 2-dimensional plot. So it is tricky to read. I suggest you to train yourselves to read it and look at other interpretations online. But it is a great it is a great exploratory tool to look at patterns between different variables. It is very standard to start analyzing your data, visualizing with your data with a principal component analysis. It tells you many things at the same time. Now, I want to spend some time to talk about clustering. That's a cool one. Personally, I just don't find principal component that cool, but clustering, I find it pretty cool. Clustering refers to finding subgroups in a data set. A subgroup will be called a cluster. Same way sometimes you have a cluster of cereals, like a nugget of cereals. We have access to a sample of size n, for which we observe p features. They're not called covariates anymore because there is no y. So here I will talk about features, not covariates. The idea is to create homogeneous groups among the observations. So you want to create groups with small variation within a cluster. You want to gather people by some sort of similarity. And the idea is it relevant to put men together and women together? Or is it relevant to put young people together and old people together? Or is it relevant to put businessmen together, like people who work together, and students together? If you are a firm that is trying to identify different markets, different demands, then this question will be particularly important. Do women buy the same way as men? Do young people buy the same way as old people? Do students buy the same as working people? Which groups are going to be relevant? That is going, of course, to depend on the type of product that the firm sells as well. We can do two things. We can either group observations that are similar according to the features. For instance, we can group people by age, or by gender, or by income level. Or we could group features that are similar according to the observations. So that's the other way around. For instance, I could group age and gender because observations in both of these groups are similar in maybe their purchasing behavior or something like that. Huge applications in marketing. Market segmentation is everywhere. If you can charge a different price to a different type of customer, a firm will try to do so. That's why you have student discounts, young kids discounts, older people discounts, and so on and so forth. Here I will talk about two different clustering methods rather quickly. I can talk about it again in the next lecture. K-means clustering and hierarchical clustering. Tough one to pronounce. Assume we want to group observations that are similar according to the features. That's just what I want to do. So we're going to create big K clusters, And each observation will be in one cluster and not another, right? So we don't want clusters to overlap. So we want to group people by how similar they are. So we want to minimize the amount of dissimilarity between observations of one cluster. For instance, you can use the Euclidean distance for dissimilarity. We know by now what Euclidean distance is. It's just a square of the difference between one person and another. So for two observations in the same cluster, you're going to compute the distance between those two observations and take the sum over all the features. So my age versus your age squared, my height versus your height squared, my income versus your income squared, and then you take the sum. That is a measure of how distant we are from each other. Now, we want to not just look at you versus me, we want to look at you versus me, but also you versus somebody else and me versus somebody else, everybody inside the same group, not just two people. So we are going to take all the pairwise comparisons, which is why we have a second sum here. The first sum here is one comparison between two people. This one is going to be the sum over all the people in the clusters. You, me, you, him, you, her, and so on. And then finally, take the average by dividing by the amount of people in the cluster. Again, with a cardinal sign. The objective is to minimize this, but this is the dissimilarity for one cluster. I want to minimize this dissimilarity for all the clusters. So, finally, I sum up over the clusters. You can see how messy it gets. First one is comparison between two people in one cluster. Second one is all the pairwise comparisons in that cluster, averaged. And third, we add these dissimilarities over all the different clusters. It is surprisingly easy to implement in the software. What you can do is you just, for each observation, you randomly give them a number 1 to k, k being the maximum number of clusters. And then in each cluster, you compute the vector of averages of the p features. You look at the average age, average income, average height, and so on. And you compute the distance between people in the cluster and that vector, which we call the centroid. You do this for each cluster. For each person, you look at his distance from the centroid in cluster 1, the centroid in cluster 2, the centroid in cluster 3, and so on. And you assign him to the cluster where his distance from the centroid is the smallest. Now, if you do this, you have to update the centroid because now somebody entered the cluster. So you have to retake the average. But by doing this repetitively, iteratively, then eventually observations will not move away anymore. You will find that the smallest distance from a centroid is from the cluster they are already in. So once they are not moving from cluster to cluster anymore, then you're done. Pretty straightforward, right? Now I only have 2 minutes. Well, I don't even have 2 minutes, but I'll take them. To talk about the second sort of clustering. So k-mean clustering requires to choose the number of clusters. And as I said, cross-validation is not something we can easily use here. We are not supervised. So it is kind of complicated. Hierarchical clustering is going to produce dendrograms. Remember what those are? They are tree diagrams. But unlike regression trees who go from top to bottom, those ones are going to start at the bottom and go up. So at the bottom, imagine the most complex tree. Each person is his own cluster. And little by little, we're going to start fusing them into making a cluster of two, and then adding somebody, or adding somebody to another cluster, and so on. If you keep doing this, at the end, everybody is going to be in the same cluster, right? You're going to fuse everybody. So of course, you're going to have to start, you're going to have to stop somewhere during the process. What's interesting about the tree that's going to be produced is that the height of the dendrogram corresponds to how dissimilar the two clusters that just fused are. So the higher clusters are fused, the less similar they are. The dissimilarity between groups is going to be a bit more tricky. I'll maybe go over this in the next lecture. But we cannot just use the Euclidean distance between me and three other person, because it's me versus another cluster. So we need to use the notion of a linkage. A linkage is a different way to compute similarity. There are 4 different types. For instance, take all the pairwise dissimilarities between me and people in the next cluster, a cluster of, let's say, 3 people. You take all the pairwise differences, and you keep the largest. And then you do this with another cluster, me versus another cluster, and then me versus another cluster again. And you will fuse me according to which dissimilarity is the smallest. Single would keep the smallest of the pairwise, average would keep the average pairwise dissimilarity, and centroid is again another measure. The point is that if I have some data that here are labeled from 1 to, is it 57 observations? No, 64 observations. So each branch here is an observation to start with. Then, when I fuse, for instance, 21 and 22, if I fuse them at this distance, at this height, this is a measure of how dissimilar or similar they are. Note that they are not as high, they are higher than these fusions. These mergers are saying that 57 and 58 are closer together, are more similar than 21 and 22 are. And then little by little, as you increase the similarities and check new clusters, you're going to have new mergers. But for instance, merging 56, observation number 56, with observation 57 and 58 shows that 56 is pretty different from this cluster because they had to merge that high at a height of 100-ish, whereas 57 and 58 merged at a height of 50. So once you do a complete leakage, you can see that the last two here produce the final data set, everybody in one cluster. So now you got to figure out where you cut. Do you cut here, where you have many clusters of two? Or do you cut here, when you have two clusters with a lot of observations? And that's another thing for you to decide. You could cut here, where you have, let's say, 7, 8 clusters, or you could cut here, where you have 4 or 5 clusters. It depends also on the amount of similarity and dissimilarity between the clusters. Here I show the example for complete linkage, but you can make the same dendrogram with single linkage, average linkage, and centroid linkage. They would produce very different clusters. So you also have to explore across methods and see maybe which clusters are repeated, which ones always show up. That would be the ones to keep. But some of them might look weird, like very vertical. And like, maybe this one is not that relevant because here it shows up, but in these other ones, it shows up way later in the fusing process. Let's conclude. I'm late. Sorry about that. And we barely scratched the surface. A lot of research has improved the methods exposed in this lecture, but the gist, the intuition, is the same overall. Couple of things to remember. Machine learning methods are very suitable for prediction problems, whether they are supervised or unsupervised. Overfitting is one of the most important problems to deal with. Every time we are trying to limit the complexity of a method, because too complex of a method would lead to overfitting and poor prediction in out-of-the-bag data, on out-of-the-bag data. Machine learning algorithms make use of data-driven procedures. Cross-validation, validation sets are data-driven. The data is telling us how we should split our tree, how we should prune our tree, and so on. And we also need to fine-tune the options in supervised problems. We use data-driven procedures to find those tuning parameters. Pruning, depth of a neural network, depth of a tree, and so on. For unsupervised problems, it is less straightforward because we do not have anything to check we are going in the right direction. And today I showed you many alternatives to the same problem, whether it's regression, classification, or unsupervised learning. So it's always good to check more than one for robustness of your analysis. And if you want to predict, use model averaging. So you can do a bunch of methods and then average the predictions out. And they are the base of AI because, again, the idea is to program an error function. Those have been all the criterion functions we've been trying to minimize or maximize for PCA or support vector machine, and improve the experience as more data come in. That's it for this lecture on machine learning methods in economics. Have a good rest of your week and see you in the next one. Bye.